Yeah, first apologies from Patrick Holz. Unfortunately, he can't come to present this presentation over here, so he sent me instead. I'm grateful for him for giving me the opportunity to actually present our work. So we're talking today about reliable numerical key rates for QKD. And basically, the motivation of that one is clear. Basically, we know for any given protocol, we can calculate secret key rates. Secret key rate is just a question, basically, how many secret bits do I get out of a protocol per channel use, right? And the thing is, of course, basically, mostly so far, we have been really working very hard over the past 2 decades to work out analytical tools to actually calculate those key rates for various protocols, right? And the difficulty of those protocols and the security proofs is actually going up, right? So basically, our problem is in a way that in the community, we just have too few people who actually can do that. Right? And so that is basically one of the things that we as well need to do something about. And one of them is basically because it's actually to make it simpler to go into security proofs. And especially as well, we need to go forward. The protocols that we're looking at are getting more complicated because they need to adapt more to actually realities in modern optical communication. And so therefore, the protocols that are of interest are changing. They're getting more difficult. And as well, we have to be careful, especially regarding side channels. We need to be able to do more refined models about our signals and our detectors, which again will just increase the difficulty of our rates. Okay, so now in this presentation, what will I do? First, I will tell you a little bit about the framework in which we are playing. Basically, what's the framework in which we do calculation of secret key rates. And basically, everything that I'm talking about today is just infinite key rates. But what we're doing over here, we see the path forward how to include finite size effects, but we have not done so yet. Then I will as well make a link to previous works that I have been actually doing in this numerical approaches, talking about the dual problem, so that you can actually see what changed since then. So I will give you the new kind of approaches that we take in the primal problem to calculate secret key rates, and then give you 3 applications to show what it is that we can be doing. Okay, let's start out with the key rates. Again, everything infinite key rate, and as well it's finite dimension. That as well connects to something that Anthony has been saying. For continuous variable at the moment, basically we would need to find some way how to break it down into something like finite dimensions. We have done similar stuff for coherent, basically in weak coherent pulse, BB84 protocols, where you have as well already similar problems because your detector is looking at infinite dimensional Hilbert spaces, but we have developing tools and techniques how to break it down to effective finite dimensional Hilbert spaces as well. And for continuous variable, we would need to do something similar. Right? So the overall goal, thanks to Renato, basically it's quite clear in the infinite key limit. Basically, we have to evaluate basically a difference between 2 entropies, which we can basically just interpret as basically the difference between Eve's ignorance and Bob's ignorance about actually Alice's data. So there are many ways actually how you could do these kind of approaches, how to execute this minimization, because we have to go basically in the worst case scenario. That's really basically what this minimization is, right? So Anthony already mentioned as well the uncertainty relations, right? The device-independent approaches of that. Basically, what I do over here is basically to go in an approach where we really go into a trusted device. That means I assume that all sources detectors are fully characterized and available to me, right? In that picture, basically, it's quite clear basically how to do a security proof. We just start out with a bipartite state, right? And then basically both parties, Alice and Bob, perform measurements and they just get classical data out of it, right? So these classical data, just by using two-way communication testing procedures, they can in principle know, right? So that means that is some constraint that we know, and that means from here, from your observation, you can actually now tell something about that this density matrices, rho AB, can only be contained in a certain set of density matrices compatible with your observation. So the next step is, of course, that you know basically what's the worst case scenario about what could Eve possibly know about. So Eve could just hold a purification of your density matrix, and that's basically the sole source of knowledge that Eve actually has, at least at that stage. Because the next thing is, of course, any QKD protocols as well contain some announcements. So we talk about the data that are in our hands, and these announcements are done over the authenticated classical channel. That means Eve actually knows all of them as well, right? And so basically now comes an important step, which is quite often, I think, overlooked. in describing QKD protocols, and very important, we do a step of a key map, where on one side, one party somehow performs a map between the local available data and the communication protocol between the two parties, and maps it into a new set of data from which we actually want to make a secret key. Once we have these data, this result of the key map, then we actually go there on error correction, privacy amplification to distill out of the result of the key map the final secret key. Right? And so the key rate over here can be now really written down just in terms of something observable over here, and that means basically we talk about here the entropy of the result of the key map. We talk about the kind of bits that need to be exchanged in error correction. And then here basically we have the whole level quantities. Here we have basically the source of Eve's knowledge, which comes from reduced density matrices of Eve's system, taking into account the announcement and all of that one. So those things basically is what we have to minimize. So overall, it's just an optimization problem, right? Nothing else, right? It's as well a convex optimization problem, so that's of course something which is always nice to have, right? And now we can think about basically, if you really look at the history of now performing these optimization for protocols analytically, basically the biggest tool that we actually have is symmetry. Right? So if you want to look and evaluate these kind of expressions over here, then you start out that the set of possible density marks compatible with your data, they can be somehow awkward formed, whatever it is. The thing is basically what we use by symmetry is just we use the symmetry of protocols and measurements. And as well, we actually, what we do, we coarse grain our observation in a kind of symmetric fashion. What do I mean by that? For example, we talk about the average error rate in the 4BBT4 signal states rather than the error rate in each signal in itself. And so that means we go to kind of observations that we, constraints that we coarse grain in this kind of symmetric way. That means in a way it gets worse. The set of possible states that we need to consider gets bigger, but that's okay because it contains for sure the worst case scenario. Right? And then basically then comes the nice thing. Once you have a symmetry over here, you can pack down, you can actually show that you need to consider only density marks that actually are invariant under the symmetry of your protocol, which is a much smaller set in the BBT4 protocol. It's only one parameter family, and then that really helps you to do the optimization. So that's basically what symmetry is doing, and basically it's unfortunately that many protocols that we want to consider in higher dimensions don't have enough sufficient symmetry to make this set over here small enough that we can handle it. Right? And as well as implementation imperfections clearly breaks that symmetry, right? Okay. So of course, so far basically what I demonstrated sounded like I'm talking only about entanglement-based protocols, but that is not the case. If you talk about a prepare and measure scheme, like I point out over here, you can actually go through the usual source replacement scheme where you think, oh, I prepare here actually an entangled state of that particular form, do here measurement in the canonical basis, then it can actually introduce now here like entanglement behind the scene between the system here before the measurement, the system here before that measurement, and ESP-ification of it, and actually gives exactly the same, fits into all the algorithm over here. The thing is basically now, actually in that principle over here, I now know basically the joint probabilities between sending a signal and getting a measurement result, but I know as well the reduced density marks in Alice's system because Eve cannot touch it in that setup. So it's an extra set of constraints that I'm having. So now, since all of it is basically an optimization problem, you can ask as well, why do I go through the effort about doing analytical proofs instead of just asking the computer, right? So things basically here, our original problem over here is just what I show here as the schematics. We do a minimization over some set with some given constraints over here. And actually what we followed before, right, in our first approach, was to go from here to the dual problem, which now becomes a maximization, a different maximization problem. We just translated one problem to the other. And the reason is basically here, the size of unknown is given by the dimension of the Hilbert spaces in here, while the dimension of that problem is just given by the number of constraints, which might be much smaller. So that is actually the aim, to go to the dual problem to make it a smaller optimization problem, right? So you have to now to maximize an expression like that, and unfortunately, basically, in order to get man, geez, this is faster than me. So in order to get an analytic expression to give the computer, you can need to make use of an inequality over here, which unfortunately turns this convex part in a kind of wild kind of optimization problem, right? But still, it's small dimensions, so we are hoping that actually will do the trick that we want, right? And so basically, the good thing is basically we don't lose from here to there to dual problems. We don't lose, we can check it. And there's actually the question whether that inequality actually, we lose something over here, is something that you as well can check. Right? Okay. Now, the problem is, of course, you might now get stuck in local maxima, and so that might actually do something bad to your key rate. Anyway, we have been able to get this first approach actually to work, and it really works, for example, if you talk about entanglement-based protocols in high dimensions. Here we use just only d equal to 5, but we can do d equal to 10 or whatever. And actually in these situations, now we can ask basically what is the signal structure. We use mutual unbiased bases. The simplest one is basically we use 2 different mutual unbiased bases in the higher dimension, right? So that is this red curve over here, that's the key rate. That is actually known analytically. And as well, basically, if you have the complete set of mutual unbiased bases for the given dimension, that one is as well analytically known as that black curve, but the curves in between were not known. So with our numerics, we very easily were able to fill in the gap over here and say, if you devise now protocols that use a different number of mutual unbiased bases, what is the secret key rate? So that works very well, right? But now it's a problem over here that we wanted to use as well this approach and apply it to the prepared measure schemes. And now you look for the primal problem. The thing is basically the number of open parameters basically depends on the scaling about the dimension. You talk about the density matrix of 2 systems, of a bipartite system, of the dimensions of here. That's the number of open parameters minus the number of open constraints. That's the number of open parameters. If the dimension goes up, that becomes ugly, right? While, of course, here the nice thing is the dual problem over here. The number of open variables is just the number of open constraints, and that might be a very small number independent of the dimension, right? But the problem, the moment you go to prepare and measure, you see actually now the number of constraints are not something only like the average error rate over 2 bases, right, which is easy, but it becomes as well, oh, but I need to fix actually what is the reduced density matrix of my system A. Right? That's the second constraint. One's observable correlation. The second is the knowledge about the reduced density matrix on Alice's system. And unfortunately, this one as well scales again with quadratic in the dimension and starts to blow up as well quite easily, right? So the dimension grow over here, and as well in this part, you lose convexity. So for that reason, we actually turn back again to the primal problem and see what we can do over here. So if you now do the primal optimization, that's basically what we're doing now. The important thing is actually we need to be careful. The dual problem basically said if you find the maximum somewhere of some function, basically you're always on the safe side if you don't find the optimal point, because that's a property of dual problems. Now we talk basically the minimum of a function like that, and if our computer does not find the true minimum, despite it being a convex problem, it should be easy, then basically we actually do statements that are not true. So you have to be very careful how now to put our primal problem in the computer that we can rely on whatever the computer tells us. Right? So we do this by a 2-step. In the first step, we just find whatever method to try to find this minimum of the convex function. Right? We don't hit it exactly, I don't care. Anything that is fast and relatively good, whatever that means. And then basically in the second step, so basically what we do then is actually to go from that part and really calculate now a lower bound on the key rate. So basically, you can start basically any optimization has usually a starting point. You get from here an approximated point. The optimum point would be over here, which somehow does not show. And basically now, for this value, that would be the true key rate that we could get over here. But basically, we did not get it. But the thing is basically now, by looking at here at the gradient and optimizing the direction, right, you actually say, basically, with the worst case gradient that I have at this solution that I found over here, you go through basically the whole size of possible density matrix until you hit the boundary. And this one gives you a pessimistic lower bound what the true key rate is. And this is actually what you get out. And this has a structure of the dual problem in the sense that this point is strictly lower than the true minimum. Right? So you're really staying on the safe side. It's very important to take this into account. We have as well the next thing, of course, we have to be worried about numerical imprecisions, all numbers that we store in our computer. Basically, all of that can do all kind of stuff. Let's say that is the set of constraints that we're talking about, or density matrix. Here's the true minimum. But then our computer, because of basically imprecision, actually optimizes over that part because the constraints are not exactly fulfilled. So the trick is basically to make sure that the computer effectively always goes through a full bigger set which contains the original set, right? And to really make sure that this one is something that will be coming out. So, and that is something that we actually do in our approach. So let's talk about some of the results so you actually see what it is that we're doing. The first thing is actually we look at the Trojan horse attack. That means basically Eve shines some light into Alice's device, out comes some reflection, which is of course much smaller amplitude than the incoming amplitude, but carries some of the phase over here. So Marco Lucamarini has been actually looking at these things about here. That is the kind of signal structures that you would assign to it. So we can do just a new security proof of the B84 with these kind of signal structures. So assuming here a qubit for the ritual states, and then this coherent state, what comes out. So what you see over here is now just a plot over here where you have here the error rates that we observe, here the key rates that we get, right? And then we basically have here, mu out is the intensity of the light that is coming back out of the system. You see basically if no light comes back over here, then of course basically all cores coincide, right? But the thing is basically now if you say if some light comes back, you see basically now something, Marco in his paper had actually been able to get some analytic results, but as usually analytic result means that you need to force some tools so that you can actually solve this optimization. Right? So he got this dotted curve over here. Then we had actually used our dual methods. This is dotted curve, which improved a little bit on that one. And actually now our primal method even improves on that one. So the important point is only we can handle those situations. And indeed, sometimes indeed, we can improve something that we lost before because of proof technique. So these things we can handle. Another important application is basically the question, basically now you have to do a B84 protocol, but your detectors have different detection efficiency. What do you do, right? The thing is all our analytic proofs fail in that scenario, right? And this efficiency might be because the detectors are inefficient or because from the outside, actually the detection efficiency is manipulated. And the thing is, again, basically you can look, P is a kind of noise parameter, extra noise in the channel. You see, again, something, yes, the analytical method to handle it to some degree, but they basically, as well, our methods improve on that one, right? So that is basically the part that we see. So basically here, the detectors are the same. Here, they are completely different. And so basically for that one, first, why would you be interested in that one? Pompong actually has a poster on that one. And for this calculation, Jan Bauer actually has as well a poster to give you more of the details. Okay, then the last thing is simply coherent states. If you use a coherent state method in BB84 where you have phase coherence rather than dephased states, similar picture over here, we can do the calculations. We get some of the improvement out of there. And G has a paper on this part over here, and it can tell you much more as well about how to use the numerics. Okay, good. With that one, let me come to the conclusion, right? So we have a new tool for evaluating performance of QKD protocols. We can do quite a bunch of side channels and different protocols that we can do. We cannot do something like continuous variable right now, because there we need, for sure, analytical tools to break it down to finite dimensions, right? But the thing is as well, overall, basically our team has been to be able to put together really one approach, how we can do numerics, so that even for new protocols, as long as they have finite dimension, as well incoming summer students can actually work on the security evaluation of those protocols. With that one, thank you very much. 2 people are here.